Hello friends, welcome to Learning Chemistry. So today we will talk about optical activity of biphenyls. You all know that stereochemistry is very important topic for CSIR, NET, GATE or IIT JAM or every MSc or BSc students for their respective board exams. Okay, so as far as CSIR, NET, GATE and IIT JAM is concerned, so questions comes from stereochemistry every year. So today I will talk about biphenyls and their stereochemistry. So let's start. So two conditions are important for biphenyl compounds to exhibit their optical activity. So first is neither of the ring should have any vertical plane of symmetry. So this means two of the rings which are present in the biphenyls, neither of them should have any vertical plane of symmetry. And the second condition is the substituent in the ortho positions must have a large size. This is because in the biphenyls there is no chiral center, okay, but the molecule is chiral due to the restricted CC bond rotation, and the chirality is due to the restricted CC bond rotation in the biphenyl. So you know that if the groups present in the ortho positions of the biphenyls are larger sufficient, so they can restrict the bond rotation around the sigma bond which joins both the biphenyl rings. Okay, so I am providing an order which tells that iodine to bromine to methyl to chlorine to nitro to carboxylic acid to methoxy to fluorine to hydrogen. This is the order. Okay, so this order tells that those groups which are higher in the order, which will have more bulkiness, and those groups will provide more activation energy barrier for the CC bond rotation. So simply means that those groups like iodine, bromine or methyl or even nitro, if these groups are present in the ortho positions of the biphenyls, so those groups will restrict the CC bond rotation around the sigma bond which connects the two phenyl rings. Okay, but the groups which are lower in the order like methoxy, fluorine and hydrogen, so if these groups are present at the ortho positions of biphenyls, so due to their lower size, so they cannot restrict the CC bond rotation. Okay, for that reason those molecules won't have any chirality on their biphenyl compounds. Now let's take a few examples so that you can easily understand the conditions, how to apply those conditions into the working compounds. So the first compound, you are seeing that if you closely look that there is no vertical plane of symmetry, because if we bisect both the rings, both the phenyl rings, there won't be any vertical plane of symmetry. There is a molecular plane of symmetry, but there is not any vertical plane of symmetry. But in the ortho positions of both the phenyl rings, there are not any groups which can restrict the CC bond. Okay, so there is no restriction of rotation. So as a whole, the molecule is achiral. So hence this is optically inactive compound. So for the next example, here you can see that in the ortho positions of both the phenyl rings, there are the groups which can restrict the CC bond rotation. Okay, but the individual groups which are both the phenyl groups have plane of symmetry which divides both the rings in equal half. Due to that reason, the molecule is achiral and optically inactive. So in the next example, you can see that one of the phenyl ring have vertical plane of symmetry. Okay, so if any of the phenyl ring is having a vertical plane of symmetry, then as a whole the compound will be achiral as shown in this example. So next move on to this example. Okay, so here you can see that neither of the phenyl rings having any vertical plane of symmetry, as well the groups which are present in the ortho positions are quite bulky, so and they can restrict the CC bond rotation easily. So this compound is optically active and obviously chiral. So let us take a confusing example, which is this, where the ortho groups there is a hydrogen and another is a sulfonic acid. So here what happens that the hydrogens have very less steric effect, but as the sulfonic group, which is polar and also have sterically bulkness very high, so that these sulfonic groups restricts the CC bond quite easily, in spite of the presence of hydrogen which have not any steric effect. But due to the steric effect of sulfonic acid in each side, so that restricts the CC bond rotation, and also these have not any vertical plane of symmetry present in any of the phenyl rings. So this is a optically active molecule. So similar example, here also hydrogen present, but tertiary butyl group is very sterically crowded. So due to presence of that tertiary butyl group, single-handedly restricts the CC bond rotation. Okay, so for that reason the molecule becomes chiral as a whole. So these are the few examples where you can select and you can determine that the molecule is chiral or achiral using the two conditions I have just discussed with you. Okay, so after deciding the molecule is chiral or achiral, if the molecule is chiral, then you have to decide there of R configuration of S configuration. There this question comes if the molecule is chiral. So now I am discussing with you so how to determine the configuration of the chiral center. So how to determine the configuration of the biphenyl, chiral biphenyl molecules, which is R or S. Okay. So we are given this biphenyl compound. So we have to determine this molecule is either R or S. Here you can see that this is bolded shaded. So this means that this carbon portion is above the plane of the paper and this is below the plane of the paper. So now we have to select which end we will look to this molecule. I will show both the ways, both the directions. So at first we will look from this end. So now what happens if you look from this end? Now we have to think that this is like an axis. Okay, so if you look from this axis, so the ortho groups which are quite bulky and there is no vertical plane of symmetry, so this molecule is chiral. Now we have to determine this is R or S. Okay, so if you look from this direction, then the nitro group which is left to this axis or arrow you can say, and carboxyl group is right to this arrow. So I am seeing these two ortho groups at first. So this is on the plane of the paper and this is the direction or arrow which is representing this. So chlorine molecule was left to the axis. So chlorine molecule is here. Sorry, not chlorine molecule, the nitro. The nitro group is on the left side and the carboxyl group is on the right side with respect to this arrow. So now if you further move here, so now this is above the plane of your paper and this is this. So this carboxylic acid will be automatically above the plane of your paper and this CH3 will be below the plane of your paper. So we will again draw another perpendicular line. So as this will signifies perpendicular to the plane of the paper, but I have to draw this in a 2D. So as this is above the plane of the paper, we have to put this in the upside, and as this is below, so you have to put this is in downside or base side you can say. So now as we are looking from this side, so we have to prioritize at first both these groups, not as a whole 4. Step by step have to prioritize. At first we have to prioritize groups within these two molecules. So you know that carbon has higher priority, nitrogen has higher priority than carbon. So nitro group has 1, carboxyl group has 2, and then we have to prioritize these two groups separately. So carboxyl group obviously have higher priority, so that will be 3 and this CH3 will be 4. And now we have to get the rotation. So 1, 2, 3. So this is S. This is how you can determine the configurations of biphenyls. And now you can argue that if we see from this side, what will happen? So that will also give the same result. So let's do this. So if we are looking from this side, so let's draw the axis or arrow. So again, this is above, this is below. This carboxylic acid is above, this CH3 is below. So let's put a vertical. So this is above, so put it upside, and this CH3 is below, so put it downside. And after that, these two groups are in the plane of paper, and with respect to this arrow or axis, nitro is on the right, carboxyl acid is left. So put the nitro group on your right to this axis, which is that, and carboxylic group on the left. So now as we are seeing from this end, we have to prioritize these two groups at first. So carboxyl group will have 1 and CH3 will have 2, and then we have to prioritize among these two groups. So nitro will have 3, carboxyl will have 4. So 1, 2, 3. So again S. So this is the way of determining the configurations. Okay, So let us do another examples similarly. So our next molecule is this biphenyl ring. So here you can check the conditions for the optical activity of the biphenyls. So here the molecule doesn't have any vertical plane of symmetry, and ortho groups can restrict the CC bond rotation along these sigma bonds which connects both the phenyl rings. So this molecule is chiral. Now we have to determine this configuration of this biphenyl ring. So now if you see from this end, write the axis, and I am seeing these two. So let's write that. Now this chlorine atom is left to this axis and this chlorine atom is right to this axis. Now you will get confused that how to determine the priority because both are Cl. Now you have to closely look that among the ortho to the Cl there is a methyl. So this Cl must have higher priority than this Cl because there is hydrogen. So methyl has higher priority than hydrogen. So the Cl which is left to the axis will have higher priority. So let's put the priority at first. So this is 1, this is 2 because both are chlorine. So we may get confused later. So I have just put the priority at first. So after that, let's take the vertical arrow. So if we come to this carbon, so you know that this nitro is above the plane. So let's put at the up position. So this carboxyl group is down. So let's put it the below. So now you know that nitro have higher priority than carboxylic acid. So this is C, this is 4. Now we have to make 1, 2, 3. So this is again S. I have done in the reverse side if you see from this side. So you can do yourself. Okay. So I am providing some examples at the end of our video. So you practice yourself and let me know your answers. And if you have any doubts, write me in the comment box. Okay. Now I will discuss about a very interesting effect regarding this stereochemistry of biphenyls, which is called buttressing effect. So what buttressing effect tells us is a striking observation when a substituent is present at the meta position with respect to sigma bond joining the biphenyl, and due to presence of that group in the meta position, the activation energy for the racemization for these chiral biphenyls becomes very high. You know that if the activation energy for the racemization becomes high, then those enantiomers which are try to racemize among themselves will not racemized, okay, because of they have to cross the barrier of higher activation energy, so they won't racemized. Okay, so this is an important effect which is called buttressing effect. So you will better understand if I explain you through an example. You can see that there is a compound A and B, where B is a simple biphenyl where ortho groups are iodine and hydrogen, and A where the similar biphenyl compounds but the meta position there is a carboxylic group. In the observation, compound A have significantly higher activation energy for racemization, which is above 21 kilocalorie mole inverse higher activation energy than the compound B. So compound A will have lesser tendency to racemize than the compound B. So this is an important aspect as far as stereochemistry of biphenyls are concerned. Not in a competitive exam, but in a board exams like MSc or BSc, this type of questions may come. You may have to explain what is buttressing effect. So I hope you have enjoyed this episode of Stereochemistry of Biphenyls. So if you have any doubt, let me know in the comment box, and also follow our Facebook page Learning Chemistry, where you can post your doubts. So like, subscribe our channel if you like the content. So thank you.